So let's do a little bit of a recap. We were talking about how if we want to talk about limits in the most formal sense, the most formal definition for limits is the epsilon delta definition, which essentially just means that a limit exists if I can draw a tolerance box around what I say it approaches and prove that that box can be shrunk down until the only thing at the center is what I claim it approaches. So it's this ability to kind of be able to tunnel in towards a limit. And that by setting up this tolerance box with variables, I can capture the idea of forever approach by handing my audience a recipe. So that if my audience says I want to be within this close of the limit to believe you, I say there is a neighborhood around X that will cut everything else greater than that distance out of the conversation. And that gives us the ability to be able to use the function to make the box, and we never have to actually touch the limit in that conversation. We just have to be able to draw the box around it. Let me do a real quick check-in. How does that storyline feel for us? Give me some thumbs up if we're feeling all right. Okay. Now, the other really, really nice advantage of that is that if all I have to do is draw a tolerance box, I don't even have to use the function I'm talking about. I just have to be able to draw a tolerance box that's allowed to shrink in and prove my limit. That gives me some freedom because now what I can use is if I'm ever working with a difficult equation, I can use easier equations as reference equations to build that box. And so long as it's allowed to shrink in forever, it's going to prove my claim. So we're going to see an example of that. Let's again remind ourselves that when we're talking about Squeeze theorem, we're just simply using some of the logic that we all feel is quite intuitive, that if there is a function below another one, that whatever I approach on that below curve has to always be below what I approach on the above curve. That in other words, if I'm dragging my pencil around something underneath something else, my pencil never suddenly skips on top. Now that works out really nicely. In truth, if we wanted to run this course properly, right, rigorously, mathematically, we would start with the epsilon delta definition of a limit, and I would actually need to go back and I would need to prove Squeeze theorem. I would need to go back, I would need to prove continuity. I would need to go back, I would need to prove one-sided limits. In fact, if you take a graduate level mathematics course, they start with this definition, and they prove everything else that we have been using for granted, taking for granted, over the past month. Because it's not about it making sense, it's about us being able to convince people who don't even believe us. And in that way, we keep it rigorous. But for this class, since we are kind of still talking about the ideas and just me trying to convince you about a different method of thinking that is logical and that is intuitive, we're not going to go back through and reprove everything. Just understand that at the basis of everything you've touched in the course, the idea of being able to build a tolerance box is at the core. All right. So let's remind ourselves about the Squeeze theorem here. So we have if f of x is less than g of x less than or equal to h of x when x is near a. Again, I say near, not at, near, because we're talking limits. Somebody remind me again of what that means. I think, Michaela, you helped me out last time. Let's see if somebody else will help me out this time. What's this mean in not math words? But
so basically, like you can just say that g has to be in between.
That's exactly what it is. Exactly right. Right? G of x is a curve that's in between two others. That's it. That's all it's saying. Now, once we have that as a given, if we can prove that the two bounding curves approach something, the same something, then what would that say about the one in the middle? Exactly right. It has to get squeezed between them so that it has to agree with this same limit, right? If I build a tolerance box around an outer curve using a upper and a below curve, and that tolerance box shrinks in, and I have a curve in the middle of that shrinking, then that must also be part of the shrinking. In other words, that's why we're calling it the squeeze theorem. It's essentially saying that you're trapping a difficult function, g of x, between two nicer functions, f and h, and then you're allowing those to squeeze in like a rock in a hard place so that the g of x function has no place to go but to agree. Think of it like a funnel. That's why we call it the squeeze theorem. So g of x, the limit, has to agree with the limit of the two things that are binding it. So let's do an example. Do we remember this curve, right? This is one of the ones we were giving as an example of a limit that does not exist. Again, somebody remind me why this did not exist. The limit as x approaches 0 of this sine of pi divided by x. Why did that limit not exist? But not just two different values. We did find at least two values. You want to go for it? Build on that.
There was no gradual change.
There was no settling in, right? There was no forever approach. Now we can make that a little bit more rigorous. Take a look. Now we can explore this with the aid of a tolerance box, right? If I'm trying to talk about the limit near x equals 0, I can look at a neighborhood a little bit to the side of it. I can draw a tolerance box that captures all the heights in that region. So I have a tolerance box whose half width is delta and whose height would need to be, well, some epsilon that's allowed to shrink forever, right? I'm allowed to shrink in this tolerance box. If I shrink this tolerance box, is the height going to be able to shrink and still contain everything? No, I can make it skinnier for sure, but even if I make it skinnier, don't I have a whole swath of heights that will be in that box? That means it's like the tolerance box is showing me there's no limit here. There's no ability for me to squeeze it down to say that things settle on a height, because that would be untrue. If I tried to squeeze this tolerance box down, there would be plenty of heights that are out of it, meaning I must not be able to pin down one place of agreement. So tolerance boxes, these epsilon delta proofs, allow us this ability to say, if I can squeeze it in forever to just one height, I've got a limit. If I can't squeeze in to only one height, I must not have a limit. So this helps us to kind of recall what's going on here. Now, again, we decided that the reason for this, or we analyzed and had insight that the reason for this is because as I get to a really small x value, the way this function is set up, it's causing me to look at sine of some bigger and bigger angle, right? Dividing by 1/100th is going to be like 100 pi, and dividing by 1/1000th is dividing by 1,000, or is multiplying by 1,000 pi. And sine of 100 pi and sine of 1,000 pi is just causing me to run rampant around this unit circle. I'm just ricocheting around it. So there's no settling point for where this lands on. It's just flipping across this thing faster and faster and faster. Now, interestingly, I've got an equation at the top here that's a little bit different. It has a similar structure where I still have sine of a constant divided by x. So we know that that thing, as I make x small, is going to cause this to whip around the unit circle like crazy, right? Again, dividing by 1/100th or 1/1000th or whatever is going to cause that part to be sine of big angles, bigger angles, bigger angles yet, which is going to mean that it's just spinning across the thing like crazy. So that is an unsettling part of the equation. This part here is quite familiar to us. This is just a parabola. So before we get too much insight, we can already kind of guess a little bit about the behavior of this. This is going to be the same sporadic behavior due to sine of x, but as x gets small, what happens to x squared? It gets what? As x gets smaller, what happens to x squared? It's getting small. So what that means is that as I approach 0, I have small parabola times crazy erratic behavior. And as I get closer, I get smaller parabola value times crazy erratic behavior. And we can already start to see that if I take this to its extreme, smallest value of parabola would be what? 0 times crazy erratic behavior would be still 0. So we have this idea of saying 0 times any crazy behavior just makes it forever small crazy behavior, right? So it doesn't matter this is ricocheting on through. Let's take a look at what that looks like if you graph it. So this is now the graph of x squared times sine of 1 over x. Notice that it still has that crazy sporadic behavior. But this time, it's going to get smaller as I approach towards 0. In fact, it's going to get smaller as I approach towards 0 in line with that parabola. We can see it as it traces. Look right here. And in fact, there's even one below it. That's quite interesting. Let's see if we can make that reveal itself as to why through the math. So first thing to notice, I'm trapped between those two parabolas. Again, I would like that to be something that I am not looking at through my eyes and recognizing. I'd like that to be something that appears through my math and recognizes. I think I've got a blank on the next slide. Let's kind of work this through. There we are. Take a look at what we can determine if we understand the properties happening with all of these different pieces. First of all, sine of x. We know that sine of 1 over x is going to have a sporadic, crazy-like behavior. However, I also know that sine of x has a limited range. What's the biggest number that can be outputted from a sine function? 1. What's the smallest number that can be outputted from a sine function? -1. So is it okay for me to say that x squared times sine of 1 over x, no matter what value I'm talking about, no matter what x value I have in there, is always going to be less than or equal to x squared times sine's biggest value and greater than or equal to x squared times sine's smallest value. How do we feel on that? Is that fair? Yeah? Go ahead.
So this was.
That we're working towards it. Yep. We haven't used it yet, but we will.
Okay, so set up the squeeze theorem. Biggest value would be the smallest value.
That's a good, I mean, it's not always, it's not the only way we can use it, but it is the way that we'll primarily use it in this class, right? In truth, I just need any reference functions, but here, trig in particular has very, very easy reference functions because our trig functions are bounded. They can only be so big and they can only be so small. Go ahead, Ed. This one right here, this one? This is a -1 over here. Yep. So I'm looking at the smallest it could be and the largest it could be, and I'm saying that it has to always be between its smallest and largest. So we'll simplify this a little bit. Notice now that means that my crazy erratic behavior function has to be between x squared and -x squared. Oh, that justifies my picture. That justifies my picture. And I can go backwards now and recognize, oh, that x squared part was just telling me about the shrinking in. The sine part was telling me that sometimes I was negative, sometimes I was positive of that magnitude. So then I get a graph that shrinks in and is bounded by that magnitude. This feels like a consistent story. Well, here's the nice thing. We already can see, again, what the limit should be. I can look a little bit to the left and right of x equals 0, and I can draw a little tolerance box that captures all of my potential heights. and I can imagine this tolerance box shrinking forever, what's it going to settle on? A height of 0. So we can already see that the limit is 0. It would already make sense that the limit is 0 because we already talked about how this thing is going to shrink in, and we're going to shrink that sporadic behavior. What we can do, though, is instead of trying to play with the limit of the hard thing, we can just say that the limit of the hard thing has to be less than or equal to the limit of the thing above it and greater than or equal to the limit of the thing below it. Right, as I trace my pencil along the blue parabola, and as I trace my pencil along the red parabola, the green squiggle is always going to be between those two pencil tracings. You got something for me?
Oh, yeah. So we want the hard thing.
What do I mean by the?
No hard thing. You saw something hard thing.
Oh, that middle function,
Yeah.
that x squared times sine of 1 over x. If you try doing the limit of that, good luck.
Yeah.
Right? So I'm not focusing on trying to do that limit directly. I'm saying I know about its behavior. It's trapped between these nicer functions. Parabolas are arguably much nicer than the whole x squared times sine of 1 over x thing. So although I want that, I am not trying to work that directly with my math. I'm trying to discover truths about it by looking at reference functions. Does that feel good?
Yeah.
Good. Anybody else? We good? So let's now take a look. If I look at just the left-hand side, just the reference function, which again just means that I can draw a tolerance box that lands on the blue and goes down to landing on the red. And we're saying that that tolerance box is going to shrink and trap all the green between it. That feels pretty good. What is the limit as x goes to 0 of negative x squared? 0. As I shrink that tolerance box on down for the red function is going to get trapped at a height of 0 as I shrink that tolerance box down. So this one here becomes 0. Again, what's the one in the middle? I have no idea yet. I haven't really done anything with that directly. And I'm not going to start now because it's pretty crazy. What about for the blue curve? Again, I can draw that tolerance box that just kind of goes up to the blue curve and a little bit sideways away from 0. If I shrink that on down, what's the only height I will capture? 0. Could we also make an argument about saying it's the same as plugging in 0? Sure. Isn't it because a parabola is continuous? In other words, I am able to draw it with no interruptions. So we can also see that continuity allows me to do that if I don't want to go through the very formal argument of epsilon delta tolerance boxes. I could just say that this right here is true because x squared and negative x squared are continuous. Well, if I have a difficult thing in the middle and it's greater than or equal to 0 and less than or equal to 0, it must be. And we were able to prove that this thing's limit is 0, and I never had to touch it. Awesome. So much better than trying to figure out how to massage and simplify that sine thing, right? Play with parabolas instead. Much easier, much, much easier. As a side note, or go ahead, yeah, let's talk on this one.
So for future problems, will it always like equal a number, or will there be times where you have to explain that it's less than or equal to a number and greater than or equal to a number?
So if we don't have so are you saying like, would there ever be a time when it's like greater than or equal to 0 and less than or equal to 10?
Yeah.
In that case, then I have not been able to draw a tolerance box that allows for forever shrinkage. So in that case, either the limit does not exist, or more likely, we just chose bad reference functions, right? Ones that did not shrink in along with the curve. Because we really want to choose reference functions that track, that squeeze, not just that are, right? Which is why, like, for example, I wouldn't just say, look, at a certain point, everything is below a height of 2. Let's just use a height of 2, because then my tolerance box couldn't shrink below a height of 2, and that wouldn't be helpful. So we always want to get something that's able to shrink in and trap, right? That proves our insight. Go ahead.
So you basically, when you do these well, if you use the right reference boxes and
Yes.
tolerance boxes,
Yes.
and this can be done not graphically, right?
Correct. What I did on here required no graph. The graph helped, which is great. Like, we should always be able to use a graph as like a resource. But I did not rely on the graph at any point in the ink that I wrote.
So how did you know that x squared would be a good reference function for the side?
Because in the original story, x squared not trapped, right? Allowed to grow and shrink pretty much without bound, right? Well, it shrinks to 0, grows without bound, right? Is this able to be trapped? What's the highest it could be? What's the lowest it could be? Then it's trapped. So I'm looking, and that's why I said oftentimes with these problems, it'll be in regards to trig functions, because trig functions, as far as sine and cosine are concerned, are trapped, right? They're trapped between an extreme range above and extreme range below. So then we say, okay, let's consider those extreme ranges and look how everything else pulls those extremes in. Good. Yeah, go ahead. Okay, about why sine can only be as high as 1 or down to -1?
So not that, but why is x squared?
It's not, I didn't use x squared as a reference, like at least that wasn't my trigger. My trigger was, this is bounded. So what I immediately did in my math is I replaced it with its bounds. Then, once I had that replaced with its extremes, I recognized I have parabolas. The parabolas are going to shrink in, so let's follow that shrinkage. So yeah, so I'm not just like reaching out into my inventory of functions and trying to choose a random thing to compare against. I'm trying to follow the natural behavior of what is this naturally bounded by, and how do those natural bounds get pulled in? Did that help? Good. Good questions. Any other questions? Okay. By the way, as a side note, because it was just such a good conversation that I had, if we go back to this example where I was at first introducing the tolerance boxes, I was actually having a conversation with Julia, and she was saying that she was trying to relate this topic to chemistry because she understands chemistry well, and she was trying to understand how this applies to chemistry. By the way, as a reminder, I love those conversations. They stretch me, they challenge me, they allow me a chance to like show you all how this is applicable for your future career and interests. And so the thing that came to my mind, first of all, how many of us have taken like chemistry in high school and or Chem 1 in college? Okay, fantastic. So a lot of you. How many of us have played with titration? A couple of us. So titration is the idea of trying to say, I want to balance by mixing solutions. So I might have a vat of acid and I'm pouring a base into it. And often you put like a little colored dye in the solution so that when you balance it perfectly, it changes color dramatically. And you go, great, that amount of solution balanced this amount of solution, I can go determine things about balancing points and ratios and concentrations and such. Anywho, this is a good example of how the same logic of titration applies here, right? If you have ever done titration, it's a difficult process. It is challenging to land that thing right on the perfect drop of solution. If you overshoot it, it changes really, really dark color right away. And if you're under, it doesn't change at all. And then every once in a while, you hit it dead on and you're like, oh yeah, that was great. Like you just hit it and it changes color and you're like, I found the perfect measurements. But then we could make an argument that it was that last drop of solution, and that what if we'd been able to cut that drop of solution in half? Wouldn't that have been even more perfect? Right? Instead of like trying to land it on one drop. One drop's a pretty good amount of stuff. And if we're talking molecules and balancing, we'd want to be even more perfect than that. So that all comes into limits, right? We can think of that as that idea of saying, I've collected a bunch of data points. All those data points are suggesting a concentration. Did we ever hit it dead on? No, it would be impossible to hit it dead on. Because to hit it dead on, I would have to balance the exact number of molecules in what I had versus the exact number of molecules that I'm adding. Like, that's impossible. We're talking way too many molecules for that to be a thing that I can hit dead on. At the same point, could I publish results that say, this group's data collection was here, this group's data collection was here, and then we all saw a trend as it got closer and closer to something, so the true value must be whatever it was getting close to. There it is, right? So what we say is that we'll publish the limit, whether any particular group actually got that value or not. Because it's not about getting the value, it's about what was everybody trending towards. That's the true value that we would be trying to hit. So just as a reminder. All right, let's take a quick look at this one before we get into the test. Again, we're just trying to do a shrinking of tolerance boxes. Again, we don't need to go exploring for reference functions. If we know how to read the equations for the behaviors they already contain, then we just use that behavior. For example, here, is square root of x bounded by anything? What? Good, right? But that would just be things I can't put in as a domain. I'm talking about heights.
No.
Yeah, it is. There we go, very good, right? The range is restricted to only those 0 and above. So we could go, okay, is that a good way to bound it? And we go, no, not excellent, because it only bounds it from below. I need to bound it in a box. Okay, so that's not going to be a great thing to bind. What about e to the x? Is that bound? What's the range of e to the x? Say again? No, the range would be simpler than that. E to the x has a curve that goes up like this, right? E to the x goes like that, right? Any negative values? Okay, good. So again, it's bounded, right? It's bounded from below. It doesn't ever hit any negative values. But again, not great for a box because I need a lid for my box, and this thing just keeps exploding off the paper. So again, that's not going to be suggesting anything. What about sine? Is sine bounded? Yes, absolutely. It's bound above and below, right? So why don't we take a look at what's happening there? So let's just immediately start to say that I've got square root of x times e to the sine of pi over x. That has to be bounded by the most extreme value, square root of x times e to the 1, and its least extreme value, square root of x times e to the negative 1. Feels pretty good, right? Just replacing sine with what it could be at least and what it could be at most. Okay. So I could rewrite that. That's square root of x divided by e, my nasty function, and then I consider the limit. Notice again, this one is a particular limit. This is a one-directional limit. Let's just double check our logic. Does it make sense that I can draw a tolerance box that only goes on one side and shrinks in? Let's check. If I say that that is my limit, would it make sense that I could draw a tolerance box that says I need to go around it, but that if I only go on one side, that would be the tolerance box, right? As that tolerance box shrinks in, isn't it still going to only land on that value? Isn't it still going to shrink to that height? So it's okay to do these even for one directional limits. So let's go ahead and do a one directional limit. Let's check the one on the very far left. As I approach 0 from values slightly bigger, right, from the positive, slightly bigger, I'm looking at 0.1, 0.01, 0.001. This thing's going to track towards 0. Don't know what the thing on the inside is yet. What about the thing on the right? As again, I'm doing square root of 0.1, 0.001, 0.00001. That's going to track towards 0. So it has to be stuck between that rock and the hard place. The limit as x approaches 0 from the positive of this big nasty thing is equal to 0 by the squeeze theorem. Going all right?